Hello.
Good to see you.
Yeah.
How have you been?
Good, but you're a bit too late.
I am. I was indisposed for a while. I got you these though.
All right.
Whole bouquet. Cool ass stuff.
Wait,
Just
careful.
check them out. Should be perfectly in good order.
Whoa, yeah, very nice.
8 of them.
Yeah, 8 of
Sorry
them.
about the delay. Turns out the only distributor of the
nice.
factory.
Yeah.
Don't really know how to work with the European market.
Nah.
Find a workaround.
Workarounds? So what was the workaround? I wonder whether these are actually work also with the other soldering iron with this one.
I can tell you that.
Yeah, because it's I mean
that conversation with Design Factory, fortunately.
Yeah, so because it's kind of the similar.
Yes, but they
it kind of snaps in.
It does. Well, take it for a spin, but maybe you have a different model of the thing. But.
Yeah, we'll try that. So anyway, that's perfect because yeah, we'll just today have a course on electronics, so we'll be able to use these maybe. Cool.
Hey,
Very nice. So maybe if we get so far today until soldering, we will be able to use these for soldering. Yeah.
Good to see there's a lot of changes around here. That's awesome.
Yeah, like things are happening.
I like your efforts on Facebook as well. Very active. Very new things are happening.
Yeah, I mean, it's interesting to post funky pictures. Yes.
Is that your project?
No, that's the this audio poly. So like a organization. So they are making a workshop where they are producing many of those. For now, I'm gonna leave these here.
Hey, quick question. Are you here tomorrow?
It's maybe, but not sure.
Wasn't really able to produce the details I wanted for the CNC today.
Yeah.
So I was wondering if by chance you are around here.
Yeah, I actually from 12 I am kind of opening the lab for these guys because they want to finish their things. Theoretically, nothing is happening with the mill, but I wanted also to kind of engage into electronics and like not being distracted at all. So, but okay, great. Then we can have a deal. Yeah. So tomorrow 12, and then we discuss the rest. But yeah, just come to tomorrow 12, and let's cut.
You're gonna keep me in the dark?
I mean, just come here and cut. Okay, that's it. Yeah, that's the deal.
Accept those terms, I'm afraid. I was hoping for something better.
Leave me alone.
Alright.
I need to focus.
Take care.
Yeah.
I don't know, maybe so. I don't know what, I have no idea why that. Every time my mom sings it, I'm not. But maybe if you have time later, I can.
All right. Here. So where your friends are coming?
No.
No? Not today. Okay. Yeah. Then so I think we can begin today. So it's the today it's going to be the last day for the for the lectures. So it's kind of the following weeks is gonna be less work for me, but more work for you. I'm just gonna guys. We're starting the lecture. So if you have a discussion, then do it somewhere else. Okay. Thanks. Wait, I need to switch off the audio here. Yeah. So yeah. So welcome. Today is gonna be the last day of the lectures. But it's one of the most exciting days, actually. I think so, because we're gonna talk a little bit about electronics. But I would like to ask you whether you read something. Okay, can you tell about it?
Only some basic information about the electronic design.
Okay.
Yes.
This book, okay. And what was it? So a bit more specifically.
Maybe about some tools during this process.
Okay.
Like the multimeter, scissors, tape, and soldering arrow,
Okay.
this, and computer.
Ah, okay, perfect. Yeah.
And maybe about the process of how to make a successful circuit.
Mm-hmm.
Yes, maybe the most important is to find parts and understand the data sheets.
Mm-hmm.
But I don't know if we have the data sheets in this tablet.
Yeah. So for every component, there's a data sheet, and we are gonna look at them today.
And I also learned about the most important part of the data sheet. Is the component operation and the electrical character is the most important part about to teach you how to design with these components.
Okay. Yeah.
And I also learned about some software during this electronic design. One is that we will use KiCAD.
Yes. Yes.
And another in this book, the author introduced EAGL. I don't know how to pronounce it.
EAGL. Eagle. Eagle, probably.
Yes.
Yeah.
And another tool is Fritzing.
Fritzing.
And VBA.
No, that I haven't heard about.
Yeah.
Yeah. I don't know whether I could do something about that. Totally nothing. Okay, we're good. So yeah, it's so maybe you can tell more about like the tools that you would use. What can you also explain a little bit more? What can you do with the multimeter and an oscilloscope? No? Okay.
I think this book is mainly about teach you how to use the software that
Just a second, I'll tell you. Guys, so there's a lecture going on. So if possible, try to avoid like making noise with this one. It's really loud.
Okay.
So I don't know, like maybe yeah, if you can go somewhere like outside and then clean up afterwards, or that would be a preferred way.
Okay.
Thank you. Yeah, sorry.
Yeah, it's mainly about the software EAGLE.
Software?
EAGLE, how to use EAGLE.
Eagle, okay.
And actually I wonder if I can borrow it face doing this level?
Sure. Yeah, you can. Yeah.
Okay, because I only read a little about this.
Mm-hmm. Yeah. Okay. So you got interested. Very good. Nice. Yeah. So then today. Okay. You did the reading. Okay. It's yeah. Okay. If you want, go on.
If you want to know, then I can tell you. But I read about these milling, CNC milling machines. I only saw some YouTube videos and on Wikipedia,
Mm-hmm.
and I got little confused maybe because there were different types of milling that happened, and whether it was the software that made the difference, or it was the setting in the engraving that made the difference. Because in the first one, it was done in flat cam,
Flat cam. Okay.
and it was a board where everything else on the copper board was removed except the circuit.
Okay.
And in the second one, there were these other three softwares like Deep Trace, and I think Deep Trace was
Deep trace.
yes.
Never heard about that.
And then he was just making a groove around the circuit and not cutting the
Mm-hmm.
whole copper board. So I don't know whether it is a setting that makes the difference, or it's the choice that I got confused in.
Mm-hmm.
And then I found out that there are, other than, I don't know if this is correct, but that's what I read, that if you do these things in the laser cutters, it is much more precise. Because the engraving has certain z-axis.
Okay, so a certain depth. Okay. Mm-hmm.
But I read it very quickly, so I'm not so very aware of what makes it.
There's another process which is acid, so which is etching with acid, so that you cover the places that you want to keep with a special paint or coating, and then you put it in a acid bath, and it eats out the copper that you don't want to have, and then you take it out. But I don't like the chemical aspect and anything that is connected with chemicals, especially in a public space like this, so that I'm kind of avoiding using those. So we are just going to stick to milling.
Yes, okay. And then there are these printers, which do everything, like they bring, then they print the circuit, then you have to cure it and then solder it. So this Volterra.
Mm-hmm.
And then there's this new one that it's very expensive, like that can print like 16 layers. The Dragonfly is extremely expensive.
All right.
In which
Yeah.
printing and curing together cost like $300,000.
All right. Yeah.
But I thought that these three types that I understood, but then the chemical one that I didn't study, and then I also saw that you could actually paste the Resistor.
Mm-hmm. Yeah, solder paste and then put it in the oven. Mm-hmm. Or you mean a multi-layer?
Yeah, and then iron.
Iron it? Okay.
I didn't read very well about that, but this is what I read.
Oh, nice. Thank you. That's good. So, I mean, like the alternative methods of what we can use here at the lab are we have a conductive filament for 3D printing, so we can actually 3D print the circuits also if they are simple, and then we have a copper foil for vinyl cutting, so you can actually vinyl cut the circuits as well. But we are going to stick to PCB milling today.
And you would still consider the engraving better for the laser?
With the laser, so the laser that we have, it's not really compatible with copper. You cannot cut metallic parts. So it's the laser is not powerful enough to pierce the copper layer. So it's going to reflect back into itself. If you would use like this fiber laser, then you would be able to do that. But with this, maybe if you cover copper with something, with some chemical, so there are some available metallic aluminum plates, for example, with special coatings that are sensitive to laser cutting. And I think it's when the laser hits the chemical, it releases acid, and the acid will kind of engraves the aluminum. Yeah, but I'm not completely sure. So yeah, if you wanna do PCB etching with the laser, then it's possible with the fiber laser. Yeah, so we are going to take like a software first approach today. Like I'm gonna show you a bit of KiCAD, so you're less afraid of it. Yeah, if you haven't downloaded it yet, then I would suggest you to download it. And then I'm gonna show you how to do milling with CopperCam software on the other computer in there. And yeah, I want to mention that there's a really nice online course on KiCAD, and it's called Contextual Electronics, and there are some introduction tutorials about it, like to start getting to Blinky. It helped me a great deal to get into it. There's some advertisements which I want to skip.
Welcome to Contextual Electronics. My name is Chris Gamble. Contextual Electronics is an apprenticeship program where you learn how to design electronics by doing. And by doing and breaking and creating and learning from all of your mistakes, that's the best way to learn electronics. This series is about KiCAD, which is an open source PCB design tool that we use in Contextual Electronics. Specifically, this is called Getting to Blinky. Getting to Blinky is the way that you know that you've started something. So in software, or with an Arduino, you know that you understand all the pieces in the tool chain by blinking an LED. In pure software, it's usually hello world. If you can get the terminal to read hello world, you understand enough about it to say that you're ready to go and move on from there. In hardware, it's a little bit more getting started, right? So to get a piece of hardware in your hand working, it's still blinking. It's still, a thing blinking. But in the meantime, you need to learn about layout, you need to learn about schematic capture, footprints, and then actually how to build stuff. And we're going to try and get you to that point as fast as possible. And in fact, we're going to try and do it faster than last time, because this is actually a remake of the original series. KiCAD has recently updated to 4.0. Previously, it was BGR 4022. It was about 2 years ago in 2013. And now we're at the point where there's a new stable release, and this is a remake to match that, because there's new features and there's some new ways of doing it. So let's take a look at how we get this thing installed and get our first project going, and then from there, we'll move on to separate videos that mirror the original Getting to Blinky series. Okay, so first things first. This is a new website, not too relevant to our needs here. But the important thing is...
I think you did that already, so we can maybe scroll forward here. So this is all for Windows. Yeah, but highly recommend. So this is a really nice course. And here, yeah, let's watch. So I think I'll use the power of the internet, and let's watch a few. Oh wait, what happened? So watch a few videos about surface mount technology. So which is so you probably have played around with breadboards and these jumper cables and things like those. And a lot of people are talking about the fact that this is very quickly dying out, so that actually the best way to start with electronics is actually to dive in and start using SMT components or surface mount technology components. Because also the latest chips that are coming out from manufacturers, so some of them are dropping so these through-hole components completely. So it's best to get started and get comfortable with soldering surface mount parts. Also, in terms of design, actually it's much easier, because then you can focus only on one side of the board, and you don't have to drill holes. Most of the time you do need to drill holes, but then you can avoid drilling holes if you just use only SMT parts exclusively. So it makes the process much faster. So let's open this first one. This is a funny one.
Solder paste may be applied to the printed circuit board by dispensing or stencil printing. A 6th thou or 8th thou metal stencil is aligned with the surface mount pads, and the solder paste is forced through the apertures using a squeegee blade. The angle and the type of the blade will be selected depending on the application. After printing, components are placed into the solder paste. Due to its tacky nature, the paste holds the components during assembly. All grid array devices are placed during the final placement operation, when other fine pitch parts are positioned into the solder paste. Accurate placement may be achieved optically with alignment of the balls and the pad locations. Optical inspection on the placement system may also check for missing ball terminations. Heat is then applied to reflow the paste between 215 to 225 degrees C to form the bond between the circuit pads and the component terminations. Reflow of the solder paste may be conducted by convection, infrared, or vapor phase reflow. During reflow soldering, the solder paste becomes a liquid. When the BGA features eutectic solder balls, these balls also form part of the joint. If high temperature balls or columns are used, they do not collapse during reflow. Depending on the product or company policy, cleaning may be conducted at this stage. Either solvent, aqueous, or semi-aqueous processes may be used to remove flux residues left from the solder paste. In the case of double-sided reflow assembly, the board is inverted to allow screen printing, placement, and reflow to be repeated. The introduction of pin-in-hole reflow can eliminate hand and waste soldering and allow reflow of surface mount components on both sides of the board. In this case, solder paste is stencil printed onto the second side of the board, printing the paste onto the pads and over the through holes. Prior to surface mount placement, through hole components can be inserted into the through holes. During reflow, both surface mount and through hole leads will be soldered in one operation. Traditional double-sided reflow is very common in modern assembly operations. As we have already seen, solder paste is printed onto the second side of the board.
This more illustrates like how the professional way of soldering surface mount components happens. So you apply a solder paste through a stencil only on the places where they are the pads, and then you put on the components and put this whole board in an oven. Then yeah, let's look at that one. Is this the same? Oh, why it's the same? Or was it video A? Sorry. Something going... Oh, wait a minute. What's that? Some kind of advertisement.
Hi, time for another installment in the Nixie Tube design video.
So this is going to be a video about how to hand solder surface mount parts. So I'm just going to skip to the part where it actually starts.
That's like to solder code, and there are no stupid manufacturer markings on the silk screen or anything like that. They haven't added their own code. I don't think there was an option to disable that. They just haven't done it, and that's great. I hate manufacturers who actually do that. It's really freaking annoying. Well, let's have a look at the silk screen first. To my eye, it doesn't look like it's dot matrix printed, but of course it is. Most of your low cost around the pad there, you can see block bench in here for expensive boards, and it's not dot matrix printed. You just see like these outlines like you would on the traces. However, solder mask expansion here. I'm not going to go in there with my microscope and actually measure it and all that sort of stuff. The alignment of the solder mask is pretty good around the pad there. You can say there's a slight offset there, but really no big deal. Can't remember what the solder mask expansion was, but that's certainly more than acceptable for a prototype. No worries whatsoever. But they haven't expanded the solder mask, so you get like a thin sliver through there. So they've done that is fine and dandy. Let's have a look at some of the via holes, shall we? Where that's good alignment of the hole based on the angular ring around there. It's almost perfect. And it's always hard to see the plating inside holes, but there it is. It does look quite reasonable.
So these are vias. So if you are making a board that has two sides, so sometimes it is that you need to cross the wires, and in order to avoid putting jumper cables, you can actually put a via, and you can continue the copper plating on the other side. So you can mill it from one side, from the other side, drill holes, and then put in these vias that you see there.
Yeah, no worries whatsoever on that. That looks like very smooth and consistent, but yeah, like you'd have to do a cross-sectional analysis, of course. This is not a professional PCB. Usually, the good manufacturers do send you a cross-sectional cut through the vias and stuff like that, so you can see the plating consistency. But everything looks nice and clean. There's no dag. There's no silk screen dags on there. There's no contamination of the board or anything like that. It looks quite good. I'm happy with that. That is certainly a pass on the electro board. No worries. Alright, so let's start out by soldering. What you're going to want to do here is always solder your low profile stuff first. So all your surface mount stuff, all your surface mount chips, all your surface mount regulators and capacitors and all sorts of other stuff. These through hole ones, don't put those in. Definitely don't put the sockets to the mixing tube. Why? Because you can lay your board flat on the bench like this, and it doesn't rock because you've got pins sticking out the bottom or anything like that. Big trap for young players. You learn that pretty quickly. That's just nicer to solder all the surface mount stuff first, and also you can get in there with your iron, of course, without these big components blocking access to pins and something like that. And certainly something like this, where you've got a big, axial resistor right next to a SO type package here, you would definitely want to do the SO package first, so you can get in there and wipe across the pins and solder those pins on the chip. So yeah, definitely do all SMDs first. Golden rule. Just checking that my chip matches the footprint. Yeah, very nice, because we did actually goof that in the original layout and had to redo it. I chose the narrow width SO package, and this is the 7.5mm wide one. So that's spot on. Let's go. And we're going to be using lead-free stuff today. None of that lead rubbish. No, I am a lead fanboy. Solder. Anyway, it's important to use very fine stuff. I've got 0.38mm stuff. You don't necessarily have to go this low, but anything under 0.5mm is what you've got. It's got 5-core Flux, genuine multi-core brand, the choice of champions, and so we'll give it a go. So that means the 5-core, of course, means that you've actually got 5 cores of flux in there. If you got that under the microscope, you might be able to see it. And the good thing about
so flux is this like a extra chemical that you add to your solder joints in order for the solder to snap better to the pads and to the components. So it kind of if you don't have solder paste, then sometimes it is that you melt the solder and it forms kind of a drop and doesn't really snap to the components. But if you use flux, then the surfaces where the flux is applied to, they pull the molten solder towards them, and this results in a much nicer solder joint afterwards.
a fine solder is that it allows you to feed in a small amount of solder onto the joint. You don't want too much. That causes too many issues with soldering. A lot of people wonder why their soldering sucks when other people do it so well. It's because you use fine solder. You control the amount of solder that you put onto the joint, and that's a big deal for surface mount stuff. You want the fine stuff, 0.5mm under. Next thing we're going to need is some flux. I've got this old Electrolube flux pen. I'm a big fan of the flux pen. We'll just
we have those.
Flux on there like that. We'll put some more over the top in a sec, but you just want a base layer down like that, so it's under the pin. So the first thing we're going to want to do is just tack down the corner pin. So we just want to feed a bit of solder onto that pin there, and then we can place it. So there we go. And we can do the pin on the other side as well, like that. So the chip is held in place, so now we can do our drag soldering. So we just put a little bit more flux there and there, just to coat the pins. You never have too much flux. Okay, now what I've got on my JBC iron here is a little weld tip. You can see the little hole in the bottom, and there's actually, you can put some solder on that. Now normally you don't want to put solder.
So we don't have these specifically. We have so I just got like these really sharp tips, and yeah, what I would recommend if you get that far to solder these kind of components, that you do like the pins individually. We have a microscope, and you can actually do that.
Onto your iron, because you can see all the flux burning off there, right? That's normally a bad thing, but we've got additional flux on there, so it's going to be okay. And these well-based ones are designed to drag soldering like this, because they sort of drag the solder back out, like sort of suck it back out of the joint as you're putting it on. So it's easier to control the amount of solder that goes onto the joint. Now, I haven't actually used this one before. This tip is brand new, and I haven't practiced with this. I think it's on the small side, but I'm going to give it a go. So this could end very badly. So we've got our solder on there, and we just want to literally drag it across like that. And that ended badly on the first couple of pins, but we can just get that off there, clean it up a bit. And we should find maybe that second last one hasn't got much on there. We'll just add a bit more solder. You see how the solder just flowed onto there? That one's got a bit too much. It's a bit how you're doing. But our well-based tip will be able to suck that back out. But ordinarily, you know, once you get this right, then you just literally just one drag across should do the trick. And just to show you that you don't need one of those well-based tips, I've got my huge, which is my general purpose iron that I use pretty much for everything. A big chisel is one of my big recommendations for soldering, even for surface mount, believe it or not. So let's try and do drag soldering like this. Just put some solder on there. I put some flux back on the pins, of course. I've tacked down the two corner pins. I've got some solder on the bottom there. Probably should put a bit more, but let's give this a whirl, shall we? See? Drag it across like that, and Bob's your uncle. A little bit of a dag in there. Yeah, you don't need a well-based tip. And by the way, that ugly stuff, you can see that's just all gunk and flux residue. That'll clean up in the wash. Geez, the alignment of that chip's a bit how you do it, isn't it? Well, let's not worry about that. Drag along, and we can do this. I'm doing it a bit slower. You can do it fast, of course. Look at that. Beautiful. What, you got a couple of little solder.
So yeah, so basically this is how you do it. So these are chips, but then so yeah, for today we also have some components. We are going to build a really simple circuit board, which will consist of a battery, a little LED, which stands for light emitting diode, and like a resistor that we will put in between the battery and the LED in order for the LED to not to burn out. Yeah, so just check it out. Then here we have the batteries, and usually when you order things from an electronics store, then you have the manufacturer number, and by using the manufacturer number and Google, you can actually find the data sheet. And this time, yeah, I had this. I really want to show this one video because I haven't really. There was some problems.
It might not take 2 hours or so. Okay, well, I just need a little bit of help with putting up everything because I've done
it and so we have this battery holder. Yeah, we are going to use this battery holder, and I got a data sheet for that. So the reason for that being that when we will get that far in KiCAD, we'll realize that there's no no footprint for that, and we are going to need to build the footprint ourselves. Yeah. And here I will need to understand which is the plus and which is the minus. Okay, these are all going to be 1. Okay. Yeah, but let's get started with KiCAD, I guess. So I'm gonna start it up. So if I go to my applications folder, so I have KiCAD, and KiCAD is not just one program. It's kind of a set of programs. And entry point is KiCAD app. And then for schematics you use the EE schema, and for the layout you use the PCB new. Then there are other tools, so Gerber viewer and some other things. I haven't really checked those out because I mostly use these two. So let's start by opening KiCAD. So here we go. It opens up this interface, which is kind of the project manager. And let's start by creating a new project. And first I'm going to choose a place where I'm going to store this, and then make a new folder, which is going to be Digital Fabrication Studio, KiCAD, demo, like so, and KiCAD demo project. So, and as you see, it created automatically with the project. It created these two files, which is one is the schematic file, and the other one is this PCB file. And in order to get started, you can click on one of those. So we need to get started with this schematic, or you can click also on this here, and it will open the schematic editor. Like so, and you can use your mouse to mouse wheel to zoom in or out. I think I'm gonna activate this mouse effect here. Yeah, it's gonna be much nicer. And you see on the right side there are all kinds of tools that you can use. So there's like, for example, power pad placement. So what we need first is some sort of a power flag. Yeah, power flag. This is going to give us entry. So even though we'll add a battery later, so the first thing that we need to add to the schematic is this power flag, which is going to define where the electricity comes from, where the electrons are flowing from. So you add this, and then pretty much like all the things in KiCAD are based not only on these icons, but it has a lot of useful shortcuts and or the so-called hotkeys, and you can access these hotkeys through the help menu. So help list hotkeys, and it makes sense to go through them and master, like a set of them. Let's say if you know 10 of those, then it's just enough. 5 even is enough. And yeah, for example, if you would like to copy this power flag, we just need to use command, not command, but the C key, duplicate. And then to add a symbol, we need to use A. Yeah, apparently for adding a power symbol, we just need to press P. And then to move it around, we need to use M. Yeah, move schematic item. But then I'll also show once you will have connections in between the components, then you'll need to use a command that stands for grab. So it's going to be easier to move the components around without destroying the connections. So power flag 1. So for plus, so usually it's plus and minus. For each of those, we need a new power flag. So I'll just add 2 of those, and you can hit escape, or you can go to the arrow here, and then you can the way how you move those, it's not by clicking and dragging. So if you can do that as well. So you can highlight those by using this rectangular selection. But if you are going to try to zoom in and drag this, it's not gonna work so nicely. So the logic how it works and how I think it used to work is that you hover it, you keep your mouse cursor over it, and you hit M, and it grabs the component that you want to move. And you can move the labels separately also, so you can. It's still going to be connected to the component, but yeah, you will be able to change its location. But then if you grab the component, it's gonna grab the so the symbol, so the labels with it. So next, in order to continue our adventure with making a circuit, so make sure that you are using millimeters again. So also here, so in this, as is in all the CAD software. So we are in Europe, we use millimeters. That's much nicer. Then yeah, so these are kind of the default settings. I'm not a big fan of changing the default settings because I'm changing software so frequently. And yeah, in order to add a new component, so you can use this one, this icon, or you can hit A. And then when you choose the tool, you need to click somewhere. And yeah, let's start typing. So battery. And actually, we are going to use a single cell battery. If you look closer to the type of, so these are going to be the batteries. So I'm not going to open the package because it's kind of a tricky package. It's all gonna fall out if I open it right now. But you saw the battery holders, which are just, you know, these metallic things. Yeah, and so single cell battery. Okay, like so. And yeah, so from here on, we can start drawing connections by using this wire tool, place wire. So what you need to do, you click on one end, then you drag, so it's creating a wire, and drag further, and you have to double click in order to finish it, like so. So I'll place the other one, click, double click to end, and I'll pick this tool in order to move these around, and I'm just gonna place it over here. So when I hit M and I move it around, so during the process I can also rotate it by hitting R, and it rotates into the angle I want. So in this case it was 180 degrees. And as you see, when I place it, when I place the components with the pins on these wires, then it automatically forms a joint, or like a junction, I guess. So as you see, like when you're starting to do things with this kind of software, then it kind of tells you the terminology automatically also. So if you forget something, as I very often do, then you can just check the under the menu, like junction. It's called junction. These are wires, and these are symbols. All right. So the next thing that we are going to use, so we want to power LED or light emitting diode. So a little light. So if you would take a look, there should be in one of the boxes. I think that the box that I gave to you. Is it? So these are resistors, but then there were LEDs inside, I think. So you can check the resistors, and then on the bottom layer, so there's in the bottom bag there are the LEDs. Yeah, in order to add those, so again you have to click on this place symbol icon, like so here, and then you click anywhere on the screen, and you start typing LED. Here you go, and it finds it really easily. I like the KiCAD search. It's so much easier than the one of Eagle somehow. And yeah, so in this symbol, what you can see, so the line here, it means that it's going to be the ground, and the other side is going to be the plus. So basically, if we ground means minus, and 5 volts mean plus. So we could connect it directly, or there's also a way how we can separate our design if it becomes complicated. So first you would add some connections like this, some wires on both of the sides, and then you would use this label tool net label, and you would click on the cable here, and let's say you would say, oh, it's going to be GND, ground, and hit OK, and it's going to give you a label.
What's the password for the computer?
Okay, you have to use your own account. Just a second, I will log in. Then Nicholas knows the password. I don't know. Yeah, you place it on the wire, and now you can connect these two. So if you place another label over here with the same name, GND, okay, and let's rotate this around, then these are going to become connected. So the same would happen if you would just draw a wire in between them, but if you're placing the labels, then it's just connected. So these are on the same kind of net. And then if you if you want to extend, if you want to move it together with the wire, with the connected wire, then you can use the G key, which, okay, you will click on the wire, so you see it. Yeah, you can drag the wire around, but in this case we wanted to drag the label around actually. Yeah, so I hit once more, and I'm dragging the label, and it's moving together with the it's extending also the wire, like so. If I would hit M, then it would move the G and D separately. I'm gonna go back, and I'm gonna hit Escape to get this selection tool. I can select all this and put it here. Yeah, and on the other side, I need to connect it to 5 volts. So I'm going to add 5-volt label, like so. Rotate it around, and grab it, so. And I need to place another 5-volt label over here, so which is going to be the plus. So I'm hitting G in order to grab it, so it aligns nicer. And another thing that we need to add in between the LED and the power source is a resistor in order to limit the current a little bit, so the current the battery doesn't destroy the LED. And I'm going to use a 100 ohm resistor this time. I'm going to go to place component, place it over here, and yeah, the symbol usually is just R. Here, okay, like this. I'm going to grab it with M, rotate it around, put it somewhere here, and add these. And actually I'm going to do it like so, that I'm going to move this 5-volt label over here with M, and I'm going to use the wire in order to connect these two. So. No, I mean, if you cannot pay now, then you cannot get the stuff. Sorry, we are not going to run around and after you.
No, but he already cut it. He already got it, you know.
Okay, and
So
why?
So
Where's Nicholas then? Can I maybe reboot? Wait a minute.
can you log into when it's like this?
Other user.
Would it be possible to send the build straight to our Junior?
Just a second.
Yeah, it's opening up, so it's no problem. So you
It could be a problem if the terminal is open on Nicholas's account, then it's a problem.
Ah, okay.
Yeah, Nicholas has opened it.
All right.
Just wait a second. Nicholas is gonna come down, and then you will say. Hey, where are you? Yeah, can you next time not log out from your account of the Cepos so that we actually can process payment? But could you just, I don't know, send me the password so I can log in and actually do that? Okay, great. Okay, see you. Yeah, just wait a second. So like for a few minutes he's gonna come down.
Oh, okay. Fine.
It is?
Yeah. You're surprised?
Yeah, because I noticed there was something weird happening. So that the holes, they were actually a bit offset, even though. So from one side it's like
Oh, actually,
it's still offset a little bit.
Yeah, but
Yeah, but let's look
I
at
was
this.
looking at the magnifier and checking like the conductivity of this thing.
Yeah, that's fine, but I'm still a little bit worried about the offset. So I don't know why it's happening. I think it's because of the alignment pins and those. So somehow they should be outside.
I forgot to check if there's actually offset.
Because you see, there's a bit more distance over here than here. But yeah, it is. Yes.
Would it be possible to create a bill to send a bill to all the union?
Whoa, yeah. Wait a minute. In order that to work,
Because someone said it might be possible.
I mean, yeah, internal invoice, but that's like extra work. It's better that you wait for 5 minutes and pay with the card and then reimburse the amount. So it's just adds extra complexity. Nobody needs that.
Okay.
So just wait a couple of minutes, please. Okay, sorry. So yeah, so we could avoid theoretically in this in a circuit simple like this, we could avoid the labels, but just for you to know, if the circuit gets a bit more complex, then you can use those. For the resistor, so we can add it component values. So you can hit on the resistor, hit E, or you can also right click and click on properties, edit properties. You see, it's the shortcut is E. And for the value, we are just gonna enter 100, like so. And you can specify the footprint, but we are gonna get to this. So 100 is gonna be just ohms. And the LED, we don't really need to specify any value. So maybe if we click on it and select. Oh no, that's the wire. I started to draw a wire. So where is it? Properties, edit properties. So value, I could LED white. Let's see. And for the battery, so I could also edit this. I wonder. So how much is it? It's 5.5 volts, or I'm just gonna quickly open the browser and type in the. So here, type in the manufacturer number, which is SR512SW, and maybe there's a data sheet. Specifications. So nominal voltage 1.5. Actually, for this voltage, we don't really need a resistor. It's a really low voltage, so the LED actually should be just okay with that. So yeah, we could avoid this, but for higher voltage, we need this. So yeah, but we got this far. So for a 5-volt battery, you would probably need this, but also we can change this to 1.5. But is it 1.5 really, or yeah, 1.55. like so, and I'm just gonna remove this one by right-clicking and hitting delete, and just connect this. So in the middle you could put a switch, but yeah, this is just a quick demonstration. So the next step that we have to do, we need to annotate all the components, so all the elements in the circuit. So as you see, there's this BT and question mark and D question mark. So we could add our own names to this, but the easiest way is to actually use the automatic annotation tool. And yeah, use these. So these are the default settings, which are fine, and you just have to click annotate. It's gonna give a message, you know, about what actually happened. So it's renamed some parts. So it annotated battery as battery 1, so BT1, LED white as D1. Yeah, and now instead of question marks, there's just numbers over here. Which is nice. The next thing is that we need to check it for electrical rules. So if all the connections are all right in the schematic. So sometimes it happens that the ends of the wires are not connected and similar things. So you click on the icon, and then you just click run, and it finished, and there are no messages, which means that there are no errors. So let's say that we are going to delete this wire here, so there's no connection, and we are going to run this check again. Run, so it's going to notify us that there's no connection. So, and it's also going to show us with a little arrow that there's no connection. So we can close this, actually take the wire, connect these two, run it again to recheck whether it's disappearing, and it is. So yeah, at the point we are good to go. Yeah, don't mind the frame so much. So it's somehow the default default canvas, so default appearance of the circuit drawing interface, schematic drawing interface. Yeah, all that matters is this place. And now, yeah, we can. So the next step is to assign these symbols to the actual footprints of components that we are going to use. So you have to click on this button, and a footprint editor is going to open. So it's also loading the footprint libraries slowly. And there are a lot of footprints in the, so kind of the default standard footprints in the library. So here on the left you see all the available libraries to KiCAD, and on the right you can see all the specific footprints that are in each library. And in the center you have you can see the actual components that we have in our circuit. And when you click on them, then the schema, EE schema, is going to try to highlight them, like so. Here. Yeah, so for the battery cell, so the interesting thing is that there is no default footprint, so we are going to need to create it ourselves, but no worries about that. So that's the fun part. I just want to demonstrate also the possibilities. So in Eagle, it wouldn't be so easy. And also in Eagle, usually when you have an electrical component, then it usually comes together with a footprint. So a schematic symbol comes together with a footprint. It's all one unit, one component, but in KiCAD it's different. So you have the schematic symbols and the footprint separately, and then you can connect those. And because, yeah, so resistors, they come in many different sizes and flavors. So if you create a symbol and a footprint for each possible resistor size, then it quickly becomes a nightmare. But with this approach, you can have a schematic symbol, and then you have 10 footprints. So 10 is probably an overkill for what you will ever use in electronics. But let's say 2 footprints, one through hole and one SM surface mount footprint that you can always assign by using this footprint assignment menu. But what you can do at this point is we can assign the LED white footprint, and for that we have here LEDs library, here, this one. And as you see, so there's so many different footprints for LEDs. So there are LED 04, 02, 06, 03, and you know, so all these flat top, I don't even know what these are, but yeah, RGB, so RGBs usually have more pins, not just 2. And then what we are going to use is this 1206, and even furthermore, we are going to use the hand soldering version, which is a bit bigger and is going to be easier for us to solder. And what you need to do is you need to double click, and you see it here. So in this, on this side of the table, you can see that it's assigned, and then you hit OK. And now also, when you click on properties and edit properties, you'll see that here's the footprint, and yeah, it's actually assigned. And I wonder, and yeah, it actually, you could assign the footprint from here, and here you can see also what the footprint is going to look like. Also, when you are opening the footprint editor here and you want to see the footprints, you can right click and click on view footprint, and it's going to open a window with a footprint editor here, and with all the necessary values. All right, so since we are missing the footprint for the battery, so we have to create it ourselves, and in order to do that, now so yeah, we need to go through this, or so there are many ways how to do that actually, but let me just figure out what would be the easiest way. So menu tools, where's the root? Oh, okay, this window here. And let me see. Yeah, here's the footprint editor. So if you go to the main project interface over here, and what you see, a new footprint editor window opens, and yeah, here are all the existing libraries. So let's say battery holders. So there are all kinds of existing ones. Coin cell battery holders, and this, yeah. So we could base off our design from this one, and in order to do so, we should create a new library, and yeah, the name of the library can remain KiCAD demo. And I'm going to click save. It's going to ask whether I want it to be global or project. So for this, we are going to select project library. If you're using the component many times, then it's a good idea to maybe make it global and store it as a separate library somewhere. And here now this footprint, it's opened. We can go to File, Save As. Hey, I'm sorry, can you have the discussion somewhere a bit, like in that room maybe?
Okay.
Thank you.
Where did the new library got created? I didn't understand. Where did the new library go?
Sorry? It's in the same folder. So basically, if you take a look at the desktop where I created the project, so it's KiCAD demo here. It's this one over here. So it's called Pretty. It has this Pretty extension. Yeah, he has this schematic, the project schematic and PCB, KiCAD PCB extension, and yeah, the library is there. And now we need to save the footprint, and let's rename it to the footprint, the name of the battery holder that we actually have the data sheet for, which is this one. Let's open over here, and if we take a careful look, then it's its name is BK335FSM. That doesn't tell us much, but memory protection devices, coin cell retainer for 5.8 millimeter diameter batteries. So we should somehow find a compromise in terms of name. So let's start with the MPD as the company name, and let's see coin cell. That's a good start, and then 5.8 millimeter battery retainer. Or retainer, I would go with older, and maybe I would add also the drawing number, or more like the data sheet. So this manufacturer number here also. So let's say BK 335. That's that. So you can look it up in the future as well. And save in library. So we need to choose the library that we just created. So the KiCAD demo here. Save. All right, and then what do we need to do? We need to follow this drawing in order to create the footprints. So I'm gonna make this smaller. Maybe put this on the sides. So arrange the windows a little bit so that we can do something right here. Yeah, and the part that we need is this one here. And as you see, there are sizes in millimeters and in inches. We can start with basically removing the drawings that are already here. We don't need those. So just zoom in and hit delete for things, or just select. I can select and delete. Reference is okay to keep, so these outlines I don't need. So we could also start from scratch, but I mean, this feels a bit safer that there are already numbered pads. I think you can also select multiple. Yeah, like so. Come on. So it's not the typical drawing program, it's not really an Illustrator, but it gets the job done. Probably faster it would be really create them from scratch. But I think they're almost done. Like so. Number one means that it's going to be the one connection. So in our case, I think it's going to be plus, depending on how you put the battery in. So I'm just gonna check the battery quickly. So, is there like also a recommendation how you would connect it? I wonder, is it going to be the plus or minus? So that we can probably decide later also whether it's plus or minus. So one of those. Yeah, so one is for one of the battery connections, so for plus or minus, and the two is for the other one. And now, yeah, let's check the. We need to yeah, we need to know the size of the pin. So it's 1.5 millimeters. And in order to change the size of the pads, we can go to properties, which you can access also by hitting E. As you can see, you can change all kinds of properties. So for example, you could also change it into a through-hole component, but you need to set the diameter. So hole size X, let's say 1 millimeter. Okay, you see it's gonna be like this, but we want it to be surface mount. So this is not going to matter. And the size along x-axis is going to be 1.52. And along y-axis is going to be 305. Okay, so yeah, it's quite small relative to the other battery holder. So we should do the same with the other one. So SMD, size X, it actually, yeah, I need to select it and then select properties, because it was the same pin. 1.52. That's position, sorry. We hit cancel. So 1.52 and 305. Like so. Okay. And then for the second pin, I'm gonna decide a little bit later, or maybe I'm just gonna set it to 4 millimeters is a bit too much. I'm gonna set it to 2 millimeters. Like so for now. Maybe 3. Looks a bit too small. And now we need to watch this distance over here. So it's 8.36. No, 38. Yeah. So yeah, and I mean, we need to understand what is the reference to these. So I'm gonna set the Y position to something. So it's minus 7.9. Yeah, and as you see, this measurement is kind of it's measuring from the edges of these pads. But what we have here is that these are measured from the center of the location. So this is the center. And if we are going to select 0 and 2, then it's going to be located over here. So you see that it's along center. So what do we have to do? We have to, in order to get the position, we have to divide this distance by 2. Or we have to rather do it like this. We have to add up the width of the pad to this distance and then divide this sum with 2. So a bit of math. So 8.38 plus 1.52 and we add parentheses to these and divide by 2, so it's going to be 4.95. So we go here. No, properties. How much was it? 4.95. So here minus 4.95, correct? Yes. Okay. And for the position x 0, and let's hit OK. And for this, we need to use the same value, but in a positive fashion, so 4.95. So, okay, so now now it's getting shape. And so we need two pads which could be assigned to these numbers, or we could actually leave them without anything. And I wonder, can I just draw rectangles over here? And not exactly on the... Can I choose the layer where I draw? No, so with this polygon I cannot. And with this one? No. So I need to place another pad, so somewhere here. And I will hit edit. And maybe I can, yeah, I can remove the pad number at all, so it's just a copper pad. And now we can make this other pad to match the size that we see here. Yeah, so let's take 1.64, it's gonna be the width. 1.64. And the height is gonna be 1.78. And I'm going to position it at 4.95, somewhere there, yeah. And then you see that there's this angle over here, so it's kind of rotating around the corner, and the angle that it's rotated to here, it's half of 71. So if you kind of divide 71 by 2, you get 35.5. So let's try to use this angle, or maybe, yeah, so because you can specify also orientation. So this was 35.5, like so. Yeah, but actually we should rotate in the other direction, and I don't think that it's the right angle anyway. It's rotating kind of clockwise or counterclockwise. I cannot really get it. So let's try to understand. So let's start with 10, 20. Okay, it's rotating counterclockwise somehow. The counterclockwise, it means that 35.5, it would be probably minus, but actually we need to subtract it from 90 degrees. I think it's going to be like this. It's going to be 54.5. Yeah, now this looks all right. So this, so the calculation I did. So here we have the angle from this center line, all right? But the way we specified the width and height is a bit different. And actually, if we flip the width and height, so let's say we add the 1.64 and 1.78 here, and we use half of 71, which is 35.5, then we actually end up with a correct angle. Yeah, so like this. Basically, we have to, what it did, so now you see if it's 0, so we have the 1.78 as width and 1.64 as height. Then we add 10, 20, 30, 35.5, and now we match this angle over here. And we hit OK. And now, so in terms of positioning, there's nothing much. So we have to use M to position it somewhere here. And if it's not possible to position it really precisely, but this seems like all right. And now, yeah, we can duplicate it. duplicate. So it has a bit different key set than the schematic editor. And I'm hitting E in order to open the properties again, and this is going to be a negative angle. And now we again can use M in order to put it in place, like so. Should be millimeters, yes. Yeah, and looks like, so the reference we could also move somewhere, right? What else? We could also add some drawings around, so around here. So in order, when we do the placement, then we don't hit the elements really. So I'm just gonna draw a line. When I'm holding down Command, then it's allowing me to do straight line. Just start it somewhere here and go like this. And yeah, it's gonna highlight the cursor with this circle whenever we want to connect something. And just double click or hit escape, and now we have the outline. Alright, so now we can hit S, Command S, and yeah, we have our footprint over here. Yeah. 1 and 2, so we can close it down. Let's go back to this. And here in the schematic editor, we can see that 1 is going to be plus, so it's going to be the side pins, and 2 is going to be the minus, or the pin in the middle. Now we can go to the footprint assignment thing again, and we can choose our library, which is here in the bottom, and there's going to be this one element. And again, we can just click on View Footprint, and we are going to get our footprint here. Just double click. So now both of them are assigned. I can hit OK. And what do we need to do now is to create a netlist, which is going to be the schematics, so how the schematic symbols are actually connected with the footprints. So there's a separate file which is going to work as an interface between the schematic editor and the PCB layout editor. I'm going to generate netlist, so it's another file in the project folder. I'm going to click Save, and then straight from the EE schema, I can go to the PCB new, or I can go to the main project editor, and I can click on the PCB editor, and it's gonna open me this one. So if I open it from the EE schema, I think it's going to automatically give me import the netlist. No, it does not. So in order so the next step, in order to import the components and the existing footprints, we need to click on this net icon, and we need to point it to the netlist file, which is in the same directory with the extension net. And then we hit OK, and we hit Update PCB, and we close. And now you see it's actually giving us all the footprints over here. So I just clicked, and yeah. So this is a really simple, really simple circuit. Yeah, and we see that this part, this side is probably where we are going to insert the battery. So we can place the actual LED pad. Put the battery cell label somewhere else. Somewhere here, and rotate it somehow like this. We are not going to use that anyway, because we are not going to print labels. But yeah, we can put it here. And we could actually draw an outline for our PCB. So it's there are enough fancy drawing tools in order to do some crazy shapes. So let's do a not so crazy one still. And when you use this drawing tool, so in order to make sure that this is actually the outline of the PCB, you should go to the edge cuts layer. So this is where the layers are. So the active layer where you're currently drawing. Then no, I'm gonna make it a bit smaller. I'm gonna make it as small as possible, like so. Maybe I'm gonna go over here. Yeah, and then in order to precisely position everything, we can move these around. Also, if you want more precision, then you can change the grid. Let's say to 5 mils, or there are values in millimeters, so you can snap it really nicely there. So yeah, so after placing the components, so I will switch back to this 0.295 millimeter grid, so we can actually draw the traces in between those. But I'm going to select, so first I will set the design rules, which is an important aspect of this PCB editor software, which is going to set what are the minimum and minimum sizes of my copper connections and vias and so on. And this you can access from here, so predefined sizes. And here you can hit on design rules, and yeah, so here you can specify those. So minimum track width, I'm going to go with 0.4 millimeters via the diameter. I'm going to go with 0.8 and 0.4. This is not important right now. Hole to hole, so also 4 millimeters. So basically minimum track width is the most important at this point. And then I will go to net classes in order to modify the default net class a little bit. So net class, it means like the so the wires basically that connect the different components. So for different wires, so let's say for power connections, you can specify a different net class which has thicker wires, and then for more sensitive components, you sometimes need thinner wires. You can specify different net classes. But usually, it's for beginner level such as ours, we just need a default one. So in clearance, since we are going to mill the PCB with a milling machine, so we need to respect the diameter of the milling tools that we have. And for this, we are going to use 0.4 millimeter tool. So the clearance in between the pads should not be bigger than 0.4 millimeters. That's the track width. Also, like 0.4 millimeters, it's good to have. Via size, via drill, micro via. So these really don't need, but I think that this D pair is gonna complain if we set it to something smaller, like the clearance value. All right, and then we hit OK. And as you see, so here the values, they change to 0.4 millimeters. So you can add more of those, but not necessarily really at the moment. And now let's click on this root tracks icon, and now you see like these white lines connecting the terminals. These are the so-called rust nets, and yeah, these are showing how the parts should be connected. So you see that this ground should be connected to that, and we can do that easily. And as you see, it's trying to suggest to you how the cable should go. So you could override that if you wish, and then we can connect this one to that, and then we also should connect that. And in order to do so, what would be the best way? So we can go around like this, or maybe like so. No, it's gonna create a short circuit, I think, if I'm do it like this. And then if you make an error, you can actually use D key, which stands for drag. You can drag these reposition quite easily. These are going to drag the other traces around if needed. So yeah, this. And here we have it. Maybe I could make this a little bit more nice, like so. Yeah, so now we have our circuit basically. You can hit save. So file. Yeah, also save a copy. And the usual way how we get this to production is that we export Gerber files. So which is yeah. So when you would send it off to PCB factory, they would accept Gerber files and then do everything themselves and send you back the boards. And here also the software that we use, it accepts Gerber files. So I got the software in order to kind of to train you in the flow of if you arrive to a point when you want to make a bit complicated PCB and you want to order it somewhere else, then you actually know the flow already. Yeah, but before you do that, I think there's one thing that you need to do. It's you need to perform this design rules check. You hit on this little bug icon and then hit run DRC. And yeah, it's gonna notify me that there's a pad close to pad, so wire close to pad. And I think these pads over here, they're basically not supposed to be connected anywhere, but still the design rule checker is somehow checking those. And basically what we can do, we can just ignore it because it's these pads actually belong to the same pins. They are all connected anyway, so nothing bad is going to happen. And yeah, so this pad and that pad, and we can so there is a way how you can just resolve it or ignore it. Was it clear marker, delete marker, run DRC? It really never happened to me, but it's fine. So these two errors are fine. So normally it would be best if you would end up with no errors, but yeah, this is okay. All right, and now we can export Gerbers, and to do so we need to use this plot icon. And we don't really need any of those except just the FCU, which stands for front copper, and the edge cuts. Plot format Gerber, yes. Output directory is going to be the same. I'll just make a new folder, Gerbers. Open it up. Do you want path relative? Yes, I want that. But let's go once more. Somehow close down the menu for some reason. But yeah, we need the front copper and edge cuts selected. We don't really need to plot footprint values, footprint references neither. PCB edge layer from other layers, yes. Silk screen actually also doesn't matter, but that's just fine. Coordinate system is fine. Zone files, yes, everything seems all right. And now we just need to click on plot. Creates two files, one for front copper and the other for edge cuts. And the next thing is to generate drills, but we don't have any drills really, so we don't need that. So we'll just close this down. And yeah, so if I go to the folder over here, I have Gerbers. Where are the Gerbers? I didn't save it in the Gerbers folder, ironically. I'll just move them there. So these are the files. Yes. And at this point, we can actually move on to the other computer where we do the PCB milling. And before that, let's just take a 5 to 10 minute break. Great, I just needed to restart the computer. No, the software, I mean, yeah. Sorry for the weird voices. Right, I just needed to restart the computer. Oh no, this is a terrible noise. Oh, wait. Sorry, I'm gonna try to add some filters for the weird voices. What did I use for the... What did I use for the other one? Noise suppression, what did I use for the gain? Sorry. What did I use for the... Okay, now? Much better, no?
The noise is a bit filtered now, yeah.
Okay, now?
Well, let's listen to it.
Okay, so this is I'm running like the studio from the other computer for the first time, so I had to reconfigure everything, and that's fine. So yeah, I'm going to copy these tool paths to a flash drive. So I don't have to specifically show that really. Gerbers, copy Gerbers, go to USB disk, and new folder, KiCAD demo. I'm gonna paste it here. Yep, and eject. And yeah, so whoever wants to see how to mill a PCB, follow me. So yeah, how was it?
I'm going for now.
Okay.
I'll keep you posted how now we have like 3 boards that I need to connect all of those 3 basically.
All right.
And then if it works, then making more of the other modules, the smaller ones.
Okay.
Let's see. Anyway, thanks.
Yeah, you're welcome. I'm happy to see it successful. So that failed. Never failed.
Why?
There was a slight offset between the front layer and the back layer. So as you see, the holes here are a bit offset. Yeah. So I could also show it to the camera. So we are talking about this board now. So as you see, there are like offset holes. Front side looks okay. No, this is the back side. This is the front side. Front side is relatively okay, but make it a bit broke, and it leaves these really ugly traces. But then on the other side, you see the traces are okay, but the holes are offset. So there is something wrong with the positioning. But then we just made another board which looks better than that. So yeah, let's switch back to the desktop, and yeah, I'm going to disconnect the mouse in order. It's this one here. Disconnect the mouse and copy over the files from the flash drive to the desktop. USB disk, KiCAD demo, copy, desktop, and no, wait, desktop, paste, should be there. Yeah, it's there. And I can close this one. I can remove the flash drive. I'll put the mouse back in. And yeah, so I'll just check if this is desktop. Yes, it is. So yeah, here we use CopperCam in order to create toolpaths for this machine. So let's open it up. So there's the previous one open. So we'll just close layer. Close layer. So let's start from scratch, like so. And well, first we need to start with importing the Gerber files. So we go to File, Open, and we start with a new circuit. And let's go to the desktop. And oh, this is another desktop. KiCAD demo, Gerbers, and let's start with the edge cuts. Open. Hit OK. There's some, yeah, so these are the edge cuts over here. Quite small, so it's a really tiny board. Then let's open additional layer and let's add the front copper. And also hit OK. Here we go. Yeah, somehow, yeah, I probably had to do it in vice versa, so I need to open up the edge cuts once more. So you start with the circuit and then you add the edge cuts. Yes, so now the only problem is that they are offset. I will need to, so here you can see the layers. So number 1 is this one, and then here number 6 is the actual outline. Yeah, and you can offset it manually, so you can just pull it over this. Like so. There are for sure better ways how to do that, but for now this is going to work. And now when that is done, we can go to File, Dimensions, and check this reframe around existing circuitry, and hit OK. And yeah, so this is going to give us the dimension of our working area that we want to, we would like to know how much area we will use on the PCP clad, on the copper clad. And in order to check these dimensions, we can click on dimensions once more, and you can see that it's 18 by 16 millimeters, so it's almost 2 centimeters. So 2 by 2 centimeters. And I'm gonna get a copper clad like that. So here are the small ones. So we can make 3 boards out of this, basically. So also I'm gonna switch over to the camera. So this one, it's like 5 by 7 centimeters or something like that. I think we have the measurement device. So yeah, it's 5 and 7.5 or 75 millimeters. So we can, yeah, like so. Yeah, let's get back to the desktop, like so. Hit OK. And now we have to select the first layer. And in this software, so an important part is to understand a little bit about the setup. So here under parameters, we can check the tool library first, which is our tool library. So number one tool is 0.3 millimeter engraver, so which with a diameter 0.3 millimeters. And yeah, it's cylindrical, so you can specify how many rounds per or revolutions per minute it will have, then how fast it's gonna go downwards. And I think I'll set it to 0.2 and other settings. And then here, like the second tool is 0.4 millimeter engraver, which we are going to use. And there are other tools as well, but I'm not gonna go over all of them now. So we need to go to this part in order to set the tool that we are going to use for engraving. So since the engraving is going to be the only operation that we are going to do now, we need to set this to tool number 2, 0.4 millimeters. And here we can set all kinds of settings, but you can leave the default settings right here. So we are going to cut only 0.1 millimeter deep. So it's just the height of the copper layer. So you're not going to cut deeper, because then it might start to become difficult to place the components. And the rest of those, they're not important because we are not drilling any holes. We are still using the cutting tool, and for the cutting we are going to use an 0.8 millimeter tool, so twice the size. Let's hit OK. Now, yeah, so is there something else?
Sorry.
Yeah.
Is the cutting tool different than the one each?
Yeah.
So you have to change.
Yeah, it's. I mean, with a bigger tool, you can go faster, and it's and faster and deeper into the material. So you can. It's safer, because the smaller tools, they might break very frequently, especially when you're starting out. And then yeah, so it's better to use that for cutting. So we select the first layer, and then we need to create traces, so our contours. We click on that, so we can specify how many times it is going to go around each of the traces. So these settings are fine, and it's going to apply to all layers, but we just have one. And you see, it's also giving us a visualization of how it's going to look like. So there are going to be some connections. But these connections here are fine, because these are connected. These are positive, connected to the battery holder frame anyway. And then this is the negative pad. And if you don't like something, you can also use these editing tools in order to remove some of the tool paths. And we can switch between. So here we can see the yellow lines are the tool paths that are so where the tool is going to go. And yeah, at this point, under the parameters, so the output data format, we are not going to touch that. So that should be that's kind of also like another topic for another lecture. However, if you are in trouble, you can click on this user's manual. It's just a PDF file with not too many pages. You can read this through, and you can actually get into really specific details in how the software works. It's very nice. And I like CopperCam, even though it's commercial software. It's developed by a developer in France, and the price of the license is 80 euros. And my imagination is that he's drinking wine, building software, making PCBs. So I'm happy to pay 80 euros so he can buy an additional baguette. So it's kind of cool. So, but I'm also in the process of looking for some open source software that we can use for this. And then now just click on machine and mill, and we just need to select the engraving. We don't have to mirror this time, so we would need to mirror if we would make a double-sided PCB, because when we flip, then basically the image is mirrored. So that yeah, we are engraving layer 1. Yeah, okay. And then we need to navigate to where we have our project files. So KiCAD demo, and I'm gonna make a new folder with milling. and this is gonna be, I'm gonna give it a name, engraving. And yeah, it's going to be interesting here now. So I'm going to save the file, and CopperCam is going to automatically add the number of the tool, so we can actually see which tool we should install before cutting. I'm going to save this, and when I go here and to desktop, I'm just curious. It is streaming desktop. Yes. KiCAD demo. Milling, so yeah, you see the T2, and T2 was the 0.4 millimeter tool. So you should get familiar with the tools that are installed in CopperCam, and then you'll be able to decode. If you're in doubt, so always double check. So go to parameters, tool library, go to number 2. You see it's going to be the 0.4 millimeter tool. The next thing, so we need also to cut it out. So we select the cutting out part, hit OK. Again, look for the desktop, KiCAD demo, milling, and let's name it cutting. Let's hit save, and let's look at the folder again. And you see it's also cutting, and it's appending the T3 tool. And if we take a look in the parameters tool library, tool number 3 is 0.8 millimeter tool over here. Let's hit OK. Like so. Now we are ready to actually. I don't think that we need this view over here. Yes. So yeah, we are ready to switch on the machine. So the actual on switch is on the back side over here. Just lift the camera a little bit. Oh, here. This one. So you have to press it. And make sure that make sure that this is closed. The lid of the machine is closed. And then after booting up, yeah, you can open up vPanel. It's on the desktop over here, and you'll be able to move the machine around like so with these arrows. And be careful with using, so these are like movement modes. So if you are selecting X100, so it's going to move 100 steps at a time, which means 1 millimeter. So 1 millimeter at a time. And it can go up to 1/1000th of a millimeter. So this is 1/10th of a millimeter, 1/100th of a millimeter, yes. Is it? Yes. Yeah, and these modes are, so when you want to really fine-tune the position, so these machines are, this is SRM-20 and MDX40, they are called more like precision milling machines for a reason, because you have this step resolution and you can cut really fine details, really small details. It's very good for PCB stuff. With a bigger machine, you won't be able to do so. Notice it has this runouts, but this doesn't have such a runout. If you go for higher rotation speeds, then it will become imprecise. But yeah, so you can move this around by using the buttons over here. Also the Z level, up and down. With the Z, be careful. So maybe if you are sure that you need to go like 3 centimeters and you are not going to hit anything, then you can use the continuous mode. Otherwise, use the 1 millimeter mode. I'm just going to move 1 millimeter by 1 millimeter. Yeah. Then there's the view button. So when you press that, it's gonna bring the tool up and bring the build plate forward, so you can examine the piece that is being cut. And yeah, let's get started with actually setting up our job. So always when you finish your activity, then remember to remove the tool and put it back where it belongs. So this is not that good. And this is the place where we keep tools. And also, if you're using alignment pins, make sure that you close this box really carefully, because we don't want them to, you know, fly around over here. There's a bag for it also. Let's put it in a bag. Yeah. And this box is generally, so this MDX box here, it's generally for, now I'm gonna switch back to the camera. So yeah, this box is for the milling bits for the precision milling machine. And yeah, just take a look at the labels. So these are the smaller ones, so 0.3 and 0.4 millimeter tools. So these are from different distributors actually. So for 0.4, we have double flute and single flute tools. Let's try out the single ones. There's a single flute 0.4 millimeter one, so let's use that. Let's put it here. And then on top of that we will need the hexagonal, so the Allen key, that you can also find in the box. So this one, it's labeled SRM-20 tool change. And here, I'll just activate this to see whether it's focusing normally. Yeah, maybe I'll move it a tiny bit closer over here. So yeah, there's a little adjustment key here you can open and thus remove the tool. So let's mill one board as for an example, and then I want to try actually to mill it. And then this soft surface is really nice to put the tool somehow. So this is an 0.8 tool actually, and it should go in one of the boxes, which is probably one of these.
But how do we know that? Does it have it written on it?
No, I just know that the last person who was cutting, he was using it for drilling, but we're gonna reuse it for cutting. So yeah, and which was where do we have the tool that I wanted to use? Oh, here, yes. Yeah, let's open it up. Careful not to break the tool. And yeah, you can examine this under the microscope in order to tell whether it's broken or not. And so I think it's fine. It looks like the length is fine. Be very careful with these, because these are really fragile, so not to drop them down. So you place it in like this. And first you place it a bit more deep in, so you leave 5 millimeters before it starts to taper. So before the angle starts there, and then you close it. And also try not to be too heavy on it, because it's more like this precision machine. The mechanical parts are not designed for high forces. Next thing is to clean the sacrificial layer. So in a similar fashion as for the bigger machine, you need a sacrificial layer, because you see there are holes in it, so sometimes the drill bit goes through, and we don't want to destroy the machine, neither the tool. So if there would be no sacrificial layer, then it would hit this metallic part, and it would be bad for the tool and probably for the metallic part as well. So we have many of those. Actually, if you sometimes experience that, this is a bit too damaged, then you can replace it. So we have a replacement once. Then we have also this tool over here. which is a vacuum cleaner. Clean the surface like this. And what else? Yeah, so yeah, now we need to put this on here, but as you see, it's, you know, we need something in order to hold it in place. And this doesn't have the vacuum bed as the bigger machine, so in order to hold this down properly, we need to use a double-sided tape. And that you can find over here. This is not this carpet tape, so this is for bigger pieces, but then here we go. This one, this yellow one, this we use. And yeah, let's just take this and apply a tiny bit of tape. And let's get a knife. Oh, let's take this. This is not that sharp, I just know. So yeah, knife. Yeah, there's. So I'm going to apply it here. Like so. So this is probably an overkill for the purpose that we want to do. So for this simple cut, so we remove the yellow part. Like so. And let's just try to put it somehow perpendicular to this edge. Like that. Parallel to the edge. Yeah, now yeah, we can move this around. We're using the arrow buttons here. And in terms of XY, we need to aim for this bottom left corner. So we just lower it down a little bit, not too much, and then move it to the corner, and then switch over to this X100 mode in order to do smaller steps. And try to move it a bit more precisely where it should be, so in the corner of the PCB, like so. And then when it's done, I need to press this XY button over here to set the origin. It's going to ask whether I really want to do so. I want to do so. And then what I'm going to do just after, I will go away from the origin I will move a little bit in to the material. So somewhere here in the middle, in order to set the Z-axis. And now I'm going to switch again to this X100 mode in order to lower the tool head. And now, so when you're driving it down, watch this gap over here. So this one here, it should be at least 5 millimeters. So go down when you see. So basically, the target now is to hit the material with the tip of the tool. But what we are going to do is we are going to actually hover it first. So we're going to go as much as low as possible now with these micro movements. We want to cut through the copper and through the material. And with this tool we are going to cut through the material. So it means that this should be like the 0 level. So actually I'm going to go like 1 millimeter up still. And now we are going to release the tool. We can hit this other button over here, which is the Z button. going to ask whether we want to change the Z origin. We want that. And just after that we can move the Z a little bit up, like so. Basically now we are ready to cut. And to do so, we are going to first close this. And then go back to our menu. And yeah, for cutting, so the best results that I have had with speed around 60, so which is the movement speed around X and Y axis, or even 50. And the spindle speed, not the highest, because when it's the highest, then it kind of overrides the recommended spindle speed that is in the specification of the machine, and starts to vibrate quite a lot. So 50 or maybe 60 for cutting, and then spindle speed one level below high, and then you click on cut. And make sure you click on delete all to remove the previous jobs. So this is the job list. And then you hit add and you go to your milling files. And do not be afraid that you don't see anything, because CopperCam produces a bit different endings for the extensions for the files. And click on the engraving and hit open. And now start cutting. So when you hit output, so this is important. You need to set the speed and the spindle speed before you load the job, because when you are going to hit the output, it's going to start cut right away. And then at some point, someone's gonna finish moving upwards into the origin. It's going to display this message, so it doesn't understand some commands in the RML file. This is because the G-code is generated for a bit more advanced machine, and there's like an instruction, probably something about the spindle speed that the machine doesn't understand, but that's okay. So all the rest of the G-code is actually fine for the machine to use. So we resume, and then it starts cutting. And successful sign of success is that it starts to, that it chips off, that the material comes a little bit off. Did you see that the material, the base material of the PCB copper clad is actually being chipped off? That means that the tool actually went through the copper layer, and everything's fine. So this is a 0.4 single flute tool. So yesterday we were cutting with a double flute one, and normally they are double flute ones. But actually for copper and plastics and things like those, this single flute, some people say that single flute is better. And for me at least, yeah, the quality of the cut is usually much better. So yeah, now it's finished. It was really fast. And then at this point we can actually hit this view button. So it's gonna give us the PCB, and open it up, and we can check the quality of the cut, like so. You see it's quite nice. I'm going to show it later in the camera, but now we can actually change the tool in order to cut it out. So, or we could actually, yeah, let's cut it out first. So what you have to do, you have to release this. I'll just rest it here for now, because we are going to make some more, so we could actually all solder the components after. And now I'm inserting the 0.8 millimeter tool, like so. And I'm going to bring the tool again to the middle of the PCB. Here. And now it's getting close. I'm switching over to 100 steps at a time, or 1 millimeter. And again, I'm going to try to move as close as possible before it hits. Maybe like this is fine. And release the tool so it falls onto the top of the surface. And fasten it. Close this down. And set the Z-axis once more. Yes. And then move up a little. And click on cut. Clear the previous path. And select this cutting file and hit open and hit output. And again, it's going to do the same in terms of the error. So I need to hit resume. And then it's going to start cutting. So it does multiple passes in a similar fashion as the box. Okay. So yeah, I think I'm gonna do this really quickly. I'm gonna remove this now, and then I'm going to go through the full cycle and show you also how the soldering works, and then if you'll have time and enthusiasm, you'll be able to try it yourself. Alright, so yeah, now I'm going to hit on view. And then, yeah, move here, open this up. So there's quite a lot of dust, so I'll use this vacuum cleaner, which currently just run out of battery. So yeah, just the brush. It's okay. Now let's use this tool in order to remove it. So as I told, like this tape underneath is maybe a little bit of an overkill, because we cut just this little piece over there. And this is it. And you can just remove it. I'll just leave the tape over on here, and then it's going to be easier to attach. Yeah, and now, yeah, let's make another break. 5 minutes. I'm going to set up the soldering station. yeah, there is my voice. Great, almost done. This it? Okay, here. So I'll make this one. What? And so we need the parts. These ones on the board. Great. Just put it here. And let's take the batteries as well. Okay, let's go. So, yeah, okay, here I set up a little station. So these are the parts. So there are the batteries. There are the battery holders in here. We have 100 ohm resistors, which we are not going to use. They are not included in the design. And these are all kinds of LEDs. So the 1206 size and all that, and then there's also a magnifying glass in order for you to be able to see through better these connections. So what I just did, I also made this sponge wet, so it's always nice to do that. And before soldering, you would hold these two keys down in order to switch on the soldering iron. And generally for SMD soldering, you would go with something like 310 degrees, or maybe 20, but 310 is fine, in order not to damage the components. And then for through-hole components, you would go 350, 370, a bit more. Yeah, geez, I think I need to refresh my knowledge in that as well. So yeah, I need a little bit of isopropanol in order to clean it. So I'm just gonna get a piece of paper or these Kim wipes. And isopropanol is somewhere in the other room. Yeah. Yeah, so this is set made last week. Enough. Yeah, you can go up to detail like this, and yeah, you can. It's double-sided, and so yeah, this is basically the detail that you can reach at this lab. So let's put a little bit more light. Yeah. So these are really small, so you need to solder them under the microscope, but it's doable. Yeah. Practice makes perfect, so to say. So yeah, what I'm doing, so I will apply a little bit of isopropanol over here, and clean this a tiny bit, so that there's no fat. This is just enough. And then I'm going to get a Flux pen. Looks like this. And when you open it up, it has this tip. It's kind of a permanent marker almost. and I'm just going to apply a tiny bit of flux onto the pins that I want to solder. So this is going to be for the holder, battery holder, and this is going to be for the LED. And now I need to remember, how was it? So I have ground here on the left side and plus 5 volts on the right side. So the outer shield is connected to the plus part of the battery. So let's take a closer look at the battery. Yeah, the packaging of those is okay, it's like that. So you open it up and then they are somewhere here inside this small battery. Look at that. Can you see that in the camera? Yeah, they're really tiny. Yes, let's take a pair of tweezers over. No, not these. Something. Oh, there's another ruler. That's kind of my favorite ruler. I didn't know that there's another one. And where are the tweezers? Ah, here they are. Alrighty. See here, so you can take one out. Yeah, let's put this back on so these LEDs, they do not escape. And let's put it back in the bag. Like so. Next thing, let's open up this package and take out one of the battery holders. So let's just take these tweezers and try to put this on top of the pads, so just to see whether we did the drawing right. And it seems that it actually not really matching. It's smaller than the pads. Oh gosh. So what do we need now? Yeah, if we take a look at the actual cuts, we could live with that. So we'll just put it over, yeah, above the. I'll need to rework check the data sheet once more and understand whether I read the values correctly. Yeah, but still, you could solder them to the pads, so plus to plus, minus to minus. The minus is somewhere connected separately, so it's not going to be in the way. It should be possible, and then the LED should fit perfectly rather. So yeah, usually you should probably double check by hand measuring these. But yeah, if it's 5.8 millimeters, yeah, it kind of you sometimes get lost in the values. And yeah, so these are this really tiny ones for the LED. Yeah, the LED fits. But what is important to understand is which of these is ground. And usually where there's ground, so there's a line on that side. There's a little green line. Here it's really hard to see, but I think it's on the bottom. Now we lost it. Found and we lost it. So yeah, this little green line on the bottom. So it's basically the ground symbol, and it shouldn't go here to the left over here. Yeah. Okay, we did enough testing, so we're going to be able to fix our error, or design error. Later on, I'm going to recheck that. As you see, it yeah, it switches off sometimes, just to eat less energy when it feels that you do not use it. And then let's follow the recommendations and let's get this really thin solder, which in this case is 0.15 millimeters. So this is inches. So where is the information about that? It's like really in inches, but it's really thin. And yeah, the idea is that first we want to attach one pad of the component. In order to do so, we need to heat up the pad and apply a little bit of solder, like so. I think this is on the way. Can you actually? It's too much light. It's not. Yeah. So you apply a little bit of solder on one end of it, and yeah, then you place the component on it. Let's double check the green. Yeah, it's okay. The pads are on this side, I think, and yeah, you put it here, and then through this magnifying glass you can really see. So my eyesight is really bad, and I'd rather do this under a microscope. So you touch the pad to heat it up, and to heat up the pad and also a little bit the component, so it snaps to the pad a little bit. I think I need to drop it on the other side. This is the correct side. And yeah, you can hold it down with the tweezers a little bit, and yeah, so it snaps really nicely. It snapped. And then the other side, it's easier, so you can take solder in one hand and the soldering iron in the other. And you try to put the soldering iron in between the part and the pad, so it heats both parts up. And if you look through the magnifying glass, so it should be smooth and shiny, the connection, like so. And then you can apply more solder to the other part, to the other side of the other pin. So you put the soldering iron so it touches both of the pins. And yeah, let's just quickly check whether we actually succeeded. So here we have the power generator over here, this one. I'm gonna switch it on, and I'm going to set it to 1.5 volts. It's fine tuning, but yeah, 1.5. Yes. And yeah, let's check. So this is plus and that's minus, right? So this should go here, and the other side should go here. And let's check. It's gonna work. Vice versa. Let's try to increase the voltage. 2.5. And 2. Maybe 2 is the magical value. Actually, you can connect it to the pads. Yeah, you see this, if I'm going to connect the battery, it should light up like this. Well, let's see. So I'm wondering if the battery is actually going to be enough. So let's see. Maybe one bit more.
Should be 1.5.
Yeah, 1.5, but let's maybe go with 1.6 and let's see what happens. Nope. 3.7. Nope. 2.1 is going to definitely work. Yes, so it means like a bit less. Yeah, it's like already fading out. So I'm curious whether it's going to work or not. So if not, it's fine. We can just get more powerful batteries. It might be that this is actually 3.3 volts. So whatever. Let's see. So first, like in order to attach this, I'm also going to use tack it down by using a little solder over here. So when you apply a flux, then this operation is really easy. So it really nicely lets you evenly distribute the solder over the place, over the pad. The next time I think I'm going to connect the camera to the microscope directly, so this, and here you go. So see, it snapped. And now the other pads on this side here. I'm going to try to bridge these. Ah, no, it actually didn't snap. Try again. Tweezers, like this. Yeah. Yeah, when the pads don't fit, then it's a bit more complicated. I need more solder. Just push it like so. Now it snapped, actually. Yeah. And in order to make it even better, I'm just going to apply a little bit of solder into all the pins once more. A little bit of flux, sorry. Yeah, and let's do it. I think I can just connect it here. Oops. It's just enough actually that we connected to one pin over here. In here. Like so. Now let's just check again with the connections over here. So this was ground. So on the bottom of pad in there it was ground pad, and then vice versa, was it? So it was a bit more in there. Ground pin. Was it vice versa? Yeah, works like that. Okay, let's see. So it means that this battery plus is up. And rolling it in, and it doesn't work. And I'm wondering, maybe I have to just flip it. Let's like stick some pliers. And put it the other way around. No, it doesn't work. Well, alright. That means that we don't have enough voltage. That's alright. Yeah, so we have to conclude that our design efforts of today have resulted with a failure, but that's alright, so we'll be able to.
Because of the.
There are two failures. No, there are two failures. I think we specified the wrong dimensions for the pads, and also there's still too much light. If I can move it closer, so yeah, too much. Yeah, the size of the pads, it was wrong, and also yeah, here you can see, yeah, the size of the pads was wrong, and also the measurements for the battery. So the battery is actually too weak to drive this sort of an LED. So you need at least 2.5 volts in order to drive it, but this is only 1.5 volts.
And would the size change of the battery?
Yeah, if we, I mean, like I have also bigger batteries. Let's see. I think if we would, there are like these bigger battery holders, but I wanted to go with the smaller ones. And yes, here we have the bigger ones.
Size changes.
And there's also a coin cell battery holder. Used to be here, but not anymore. And I wonder. So I think these batteries. Let's just check. I'm gonna make a set of jumper cables, and maybe if we get this battery to work. So plus, it doesn't tell really how many volts is it, and this is where we can use a multimeter actually to measure voltage of the battery. I wonder does it work or not. It's off. In order to measure voltage, we need to set it to a certain mode, which is somewhere. This one, so it's it's going to measure up to 20 volts, and the top part is plus and the bottom part is minus, and it has not so much voltage, it has only 0.5. In this small one, you measure it. This is 1.5. Yeah. So yeah. And for example, sockets. Yeah. That's not going to work so quickly. Yeah, but basically, we would do another iteration, we would fix the errors, and it would work.
I think it's quite easy to do that.
Yeah.
I wonder, but we checked the dimensions.
Yeah.
Didn't we? So how?
Not really. So I didn't check the dimensions at the end. So I was relying more on the drawings. But the drawings, I am afraid that I actually used the wrong values. So the distance 7.
Was there a possibility to cross-check those measurements where we drew them? Like, give dimensions.
8.38. I think where I went wrong, or I think I know where it went wrong. It went wrong with this distance, because I was adding those up, but I had to subtract actually. I had to subtract from this value. I had to subtract the width of the pin, But I actually added it up and then I divided by 2. So
Yeah,
that was the
you
first issue.
subtracted, but the division was not needed after.
No, division was needed, so I had to split this in 2 in order to calculate the right distance from the center anyway. But then instead of removing this, this distance from it and then dividing, I was adding it up. So it's actually visible there. I mean, in a minute we could fix that. But yeah, this is not going to fix our issue with the LED.
No.
But maybe, I wonder, maybe we have some LED which is actually capable of working with, so this is, 3, and this is 2 to 2.2 volts. Let's check, maybe we have something else. But otherwise, yeah, I'm gonna stop streaming here, and let's explore that without the camera.